to figure out where this line is closest to 1, 1. So as we discussed in the last video, we have this line that's 1, 2, 3, 4, 5 as its y-intercept, and then it goes down 2 and to the right 1, down 2 and to the right 1. So this is the visual of this line, and then we have the point 1, 1. So if we're going down 2 to the right 1, down 2 to the right 1, our 1, 1 point is here, and we want to minimize the distance from 1, 1 to this point on the line. So to this point x, y that is on the line. So this question is a question of minimizing the distance between the line y is equal to 5 minus 2x and the point 1, 1. And that question of minimizing the distance is really the same thing as minimizing the distance between x, y and 1, 1, where this y has a coordinate or has a function definition of 5 minus 2x. So what we will do is we will write out our distance formula, which is the square root of, and remember it's our x2 coordinate minus our x1 coordinate quantity squared, plus y2 minus y1 quantity squared. So here our 2 points of interest are xy and 1, 1. So what I'll have is I will have, and I always just kind of put the variable one first, so x minus 1 quantity squared plus, and then y minus 1 quantity squared. Now, this is subject to the constraint that you are on this line, that y is equal to 5 minus 2x. So if you want to think about it this way, you're subject to the constraint of 5 minus 2x. All right, so I'm going to plug in that constraint of 5 minus 2x minus 1 quantity squared. And then I would just simplify and say, okay, this is going to be x minus 1 quantity squared, and then plus, here I have 5 minus 1, so that's going to give us 4 minus 2x quantity squared. All right, now we talked about in the last example that if you minimize your distance, that is the same as minimizing distance squared. So if I square both sides, that is going to be an equivalent problem, and it is going to be a little easier to deal with that simply in terms of taking the derivative. So what I will do is I will say that d squared is equal to x minus 1 squared plus 4 minus 2x quantity squared. And then at that point, I take the derivative and then find my critical numbers, because this is my objective function. So if I take the derivative, I get that I am looking at general power rule here, general power rule here. So 2 times x minus 1, the derivative of the inside is just 1, plus 2 times 4 minus 2x, derivative of the inside here is negative 2. Now, we want to find our critical numbers, so we're going to take our derivative and set it equal to 0. Now, what I kind of would think about in terms of solving this, you could factor out a GCF of 2, or you could distribute the 2's. It kind of depends on how you want to approach it. So I'm going to distribute the 2's here, and then notice that this 2 times negative 2 gives us negative 4 times 4 minus 2x is equal to 0. Distribute the negative 4 yet again to get negative 16, and then plus 8x, and then here I have a negative 2 and a 2x is equal to 0. So this is then going to give us a 2x, and an 8x is going to give us a 10x, and then a minus 18 is equal to 0. And this again is my first derivative. So if I solve, I get x is equal to 18 over 10, which of course can reduce to 9/5. So our x coordinate is 9/5. And if we want to verify that that truly does minimize it, what we would do is we could use either the first derivative test and draw the number line, or we could use the second derivative test. And here the second derivative test is very straightforward, because if you look at your first derivative in its simplified form, you have 10x minus 18. So the second derivative would just be 10. That tells us that it's positive, so that means that it's concave up. And if it's concave up, then we do in fact have a minimum at that x is equal to 9/5. So x is equal to 9/5 does minimize this function. All right, now as we know, we cannot just leave it at x is equal to 9/5. We have to go back to our constraint and use our constraint to find the other variable. So our constraint here was y is equal to 5 minus 2x. So I'm going to plug in the x value of 9/5. And then that's going to give us 5 minus 18/5. Get a common denominator here. Multiply by 5 over 5. That gives us 25 minus 18. So we get 7/5 as the y coordinate. So our answer here is the point that minimizes that distance where the line is closest to 1, 1 is 9/5, 7/5.